Okay, I'm going to go through the chi-squared analysis for the Wisconsin Fast Plants lab that was giving us a little bit of problems in class. I went through the numbers with Mrs. Wegman, and it makes a lot more sense to me now, so hopefully I can help you make sense of it too. All right, we should have about the same data for these first couple of steps here. The phenotypes are purple standard, purple dwarf, green standard, green dwarf. The expected ratios were 9 to 16, 3 to 16, 3 to 16, and 1 to 16. Those ratios came from us completing our dihybrid cross. The expected number of plants was 15, 4, 4, and 1 because everybody had 25 seeds. What we did with these numbers is we brought it up to 200 seeds total for all of the classes, so 2 classes. 4 groups in each class, 2 classes total. So 15 times 4 times 2 was 120, 4 times 4 times 2 was 32, 32, 1 times 4 times 2 was 16. That brought us up to 200 seeds total. This was our expected outcome, what we expected to see based off of the dihybrid cross. Our observed data for purple standard, purple dwarf, green standard, green dwarf, the ratios were 10 to 4 to 5 to 4. And then our observed number of plants was 72 purple standard, 61 purple dwarf, 41 green stem standard, and 26 green stem dwarf. Just looking at this critically right now, these numbers are very different from the expected outcome. The observed was 72 purple standard, and we expected to see 120. That's a big difference. The observed was 61, the expected was 32, 41, 32, 26, 16. So our observed plant data was very different from our expected plant data. The next table, step 3, just has us filling in these numbers again to help us with our chi-squared calculation. So the chi-squared calculation is going to be the sum of the expected outcome minus the observed outcome squared divided by the expected outcome. That gives us our chi-squared. And then when you plug that into a chi-squared table, you look at the degrees of freedom, which is your sample groups minus 1. So our degree of freedom here is going to be 3. And then we want our p-value to be 0.05 because that's going to give us a 95% accuracy. And I'll explain that when we get to that part. So just stick around for a second. Again, just crunching these numbers here. Expected was 120, observed was 78. That gave us a negative 48 deviation. We square that and we get a positive 2,304. We take that 2,304, divide it by 120, and we get our 19.2 value right here. 32 for the expected value, 61 for the observed to give us a deviation of 29. Square that, we'll do 841 over 32 to give us 26.28. Expected was 32, observed was 41. Subtract, square it, get our squared number, divide it by 32 for 2.53. And again, for the green stem dwarf, we expected 16, we got 26. That gave us a deviation of 10. Deviation squared is 100. 100 divided by the expected, which was 16, gave us 6.25. We add these 4 numbers together. That's the sum. We add these 4 numbers together, and we get 54.26. That should be, your number should be around there. This is a really big number, and we started freaking out a little bit because the practice problems that we've done, the practice problems that we've completed have given us a much smaller number. So in our practice problems, we've been failing to reject the null hypothesis. But when we look over here we're going to be able to explain what's happening. If we have our degrees of freedom being 3, because we had 4 phenotypes, degrees of freedom is going to be 4 minus 1, which will give us 3. We want to be 95% certain. So to say that if the probability value is 5% or greater, then your results support the null hypothesis that there's no difference between the observed and expected values, or there's a slight difference caused by chance. All right, a slight difference caused by chance. So we would expect, if our number was smaller than 7.815, that there was no difference, or the difference was caused by chance. If the probability is less than 5%, so going out this way, so less than 5%, 1%, 0.5%, 0.1%, going this way on our graph. We're going to keep going this way until we hit the number 54, right? That means we're going to have a much less than 5% chance that our results do not support the null hypothesis. And the difference is due to something else, some other factor. We reject the null hypothesis and conclude that the difference between our results is not due to chance, but some other factor. And the difference is statistically significant. All right, that feels like a lot of doublespeak. Fail to reject. So let's read this together again. If our probability value is 5% or greater, 5% or greater, 5% or greater means our chi-squared number was nice and low. Then our results would support the whole null hypothesis. We would say there's no difference between the observed and expected values, and or if there was a slight difference, it's caused by chance. So if the number that we got 54 something, but if we got something nice and low, like 7.8 or lower, we would say that there's no difference between the observed and expected. There was no statistically significant difference. However, our number was 54 something, so we are way over this way. The probability is less than 5%. So here's 5%, here's 1%, 54 is all the way down here somewhere, okay, 0.000 something. If the probability is less than 5%, then your results do not support the null hypothesis. The difference is due to chance. Instead, we reject the null hypothesis and conclude that the difference between your results is not due to chance, but some other factor, and the difference is statistically significant. So what does this mean for us? What does this mean for us? This means our experiment, our seedlings, grew with phenotypes that were very different than what we expected to see. So what you are going to have to demonstrate in your lab, you're going to have to demonstrate and analyze why you think this happened. What do you think could have happened? How could we improve this experiment in the future to see if we end up with results more aligned to our expected outcomes? Or what would we change to end up with results more aligned to expected outcomes? Or how could we account for these differences? What could have happened here? 200 seeds is a fairly decent sample size, but maybe when you're looking at variabilities like this, it is still too small of a sample size. These are questions that you're going to have to analyze in your lab report, and I don't expect you to come up with an answer per se, but I do need you to think critically about what we could do differently if we were to conduct this experiment again, and why do you think we ended up with results that were statistically significantly different from the expected outcome. Okay? So I hope this clears things up for you. I know this was a long video, and we can talk more about it Hopefully I'll see you next week. We're expecting a lot of snow, so we'll see what happens. Go Birds.